Hi all. First of all, I would like to thank the organizers for giving me the opportunity to talk here. So I'm going to talk about knot theory in overtwisted manifolds. And this will have two parts. In the first part, I will be talking about motivation, some background, and a brief history. And the second part will be more focused about on the recent work. And this will be a joint work with Environment and Mukherjee. Okay, so I'll start with the motivation. In contact world, we have this nice dichotomy, which is tight contact structures versus over-twisted contact structures. So for now, I'm not going to give you the definition of the tight or over-twisted contact structures. So let's just put a black box around it. But what I'll say you now that in literature, tight contact structures are those which have the spotlight on them. So people are really interested in tight contact structures. People care about them a lot. And the reason is that the classification of tight contact structures or existence of tight contact structures is a really interesting problem in contact geometry. So what about the over-twisted contact structures? Are they neglected? That's the obvious question, right? But the truth is no, that's not true. So we have actually Eliashberg's fundamental result, and this is a result from 89, which says that over-twisted contact structures up to isotopy are in one-to-one correspondence with two plane fields up to homotopy. So if we understand this homotopy class of two plane fields, we completely understand over-twisted contact structures up to isotopy. This is a very, very celebrated result in contact geometry. The second result is by Gom. So what Gom says that D2 and D3, these are two obstruction classes of two plane fields. They completely classify two plane fields up to homotopy. What are these D2 and D3 invariant? D2 and D3 invariant basically measures how the two plane fields are different on the 2 skeleton and on the 3 skeleton. So if you have two plane field and the D2 and D3 are not the same for those two plane field, then they cannot be homotopic. And so by Eliashberg's result, they cannot be isotopic as over-twisted contact structures. So if you take Gom's result and Eliashberg's result together, that means D2 and D3 invariant completely classify over-twisted contact structures, and we are done, right? But our focus is on knots in over-twisted contact manifolds. How much about these knots, how much we know about these knots in over-twisted contact manifold, or how are they different from knots in tight contact manifolds? That's the question. You might be thinking that, okay, if over-twisted contact structures are completely classified, then maybe the knots in them are not that interesting. But it turns out, no, that's not the case. In fact, the knots in over-twisted contact manifolds are very, very mysterious and very, very non-trivial, their classification. And also very less explored. We don't know pretty much a lot about these. Like, we do not know mostly a lot about these knots. So today, I'm going to talk about these two main themes of knot theory in over-twisted manifold. The first one is a classification. So what we know, or what knot types are kind of classified, or if how they are different than the tight ones. And the second one is the structure theorem. By structure theorem, I mean that how the geometry of these knots change under the certain topological operations. And you'll see that that will be very, very different than the knots in the tight ones. Okay, so now starting with some background. A contact structure on a 3 manifold is a nowhere integrable 2-plane field. By nowhere integrability, I mean that the contact planes twist at every point. So you can never find a surface in the 3 manifold where the contact planes will be tangent everywhere. So we have this two types of contact structures, tight and overtwisted. On the left-hand side, we see the picture. This is the most common picture of a contact structure. This is R3 with Z standard. This is the standard tight contact structure on R3. And as you can see that along the y-axis, the contact lens twist in a left-handed fashion. And contact structures are defined as a kernel of a one form. So this particular contact structure is defined as a kernel of dz minus ytx. On the other hand, this other picture on the right-hand side, this is also an example of a contact structure on R3. And in this one, if you move from the center to radially outside, you'll see the contact lens twist. But the main difference from the tight one or the left-handed picture is that the planes are twisting excessively. And this particular one is defined as a kernel of this one form. So I haven't given you any definition of an overtwisted contact structure yet. But from this picture, you should guess that the main difference between tight and overtwisted is that the contact planes in the overtwisted twist excessively compared to the tight ones. Okay, so now the definition of contact manifold, an overtwisted contact manifold. So contact manifold is overtwisted if we can find an embedded overtwisted disk in it. And what is an overtwisted disk? Here's a picture of an overtwisted disk. So along the boundary of the disk, the contact planes are tangent. So if we can find such a disk embedded, this is important. It must be embedded. If it's immersed, then it won't be. It won't do our work. So if it is embedded, then we call it an overtwisted contact structure. Okay. Now knots in contact manifolds. So there are two types of knots in a contact manifold: Legendrian and transverse. There's a local picture on the left-hand side of a Legendrian knot. So you can choose any point on the knot, and if you draw a tangent vector, you'll see that the tangent vector actually lies on the contact plane. And this is the definition of a Legendrian knot. A Legendrian knot actually lies on the contact plane. And for transverse, if you choose any point on the knot and then you draw a tangent vector, that will be transverse to the contact plane, which is the definition of a transverse knot. Okay. Now, if I'm talking about knots, I must tell you what are the classical invariants of these knots, so that the invariants which can tell these knots apart. For Legendrian knot, we have two classical invariants. The first one is known as the Thurston-Bannequin number, in short TB, which measures the difference between the Seifert framing and the contact framing. So we need a Seifert surface to define the Thurston-Bannequin number. But well, there are also ways to define the Thurston-Bannequin number without Seifert surface. There are relative versions, but let's not go into it. There is a second classical invariant of a Legendrian knot, which is known as the rotation number, or in short, rot. This is the winding number of the vector field with respect to the trivialization of the contact structure when you restrict it to the Seifert surface. So again, we need a Seifert surface to define a rotation number. Okay. Now for a transverse knot, we have just one classical invariant, which is the self-linking number. Now the self-linking number is the linking number of this transverse knot T with T prime. This another knot T prime. Now, where is this T prime coming from? Now, T prime is a knot coming from pushing T in the direction of a specific vector field, which lies on the contact plane. So here I have the transverse knot, and these are the contact planes. And here I have this vector. So if I push the knot in this direction, we get another knot, and then we compute the linking number of these two knots, which will give us the self-linking number. Okay. Now, is there any relationship between a Legendrian and a transverse knot? This is a very, very important thing in contact geometry. So by keeping the knot type fixed, we can move from a Legendrian knot to the transverse representative of the same knot type. So there is this operation which is known as the transverse pushoff. So if we have a Legendrian knot, we apply the transverse pushoff, we get a transverse knot. And if we want to go from the transverse knot to the Legendrian knot, then we apply this operation, which is known as the Legendrian approximation. So a Legendrian approximation gives us a Legendrian knot from a transverse knot. Now, what is the problem? The problem is that while a transverse pushoff is unique, the Legendrian approximation is not unique. So if you apply transverse pushoff, you get exactly one transverse knot from a Legendrian knot. But if I have a transverse knot and I apply Legendrian approximation, I can get lots and lots of Legendrian approximations. So that could create a problem. But the good news is any two Legendrian approximations are related by an operation which is known as the negative stabilization. So a negative stabilization is a local operation on a Legendrian knot. So if we have a Legendrian knot like this, negative stabilization will be like this. So adding just a zigzag like that. So that will give us a negatively stabilized Legendrian knot. Okay. Now, classification of knots in contact manifold. So there are two types of classification of knots, like two basic kinds. The first one is the Legendrian isotopy. Of course, by the name, you should guess this is the strongest classification, because in this isotopy, we have to keep the knot Legendrian at every point. So this is the strongest notion of classification. The second one is the contactomorphism type classification. That means there exists a contactomorphism which takes one knot to the other. And of course, this is not strong as Legendrian isotopy. But in S3Z standard, which is the standard tight S3, these two notions are the same. So if you can prove any classification up to contactomorphism, that is also same as Legendrian. They are also same as Legendrian. They are also Legendrian isotopic. So that's why that's in S3 standard. If you're working with S3 standard, life is a little bit easier. But in general, these two notions are not the same. So if you are in a general 3 manifold, or if you are in S3 but not in the tight S3, say in an overtwisted S3, then the contactomorphism type is a lot weaker notion of classification. So we use a third type of notion of classification, which is known as the coarse equivalence. So what is a coarse equivalence? Coarse equivalence is like contactomorphism again. So we have a contactomorphism which takes one knot to the other, but this is also isotopic to the identity. But again, coarse equivalence is not as Legendrian isotopy. So if you can prove that two knots are coarsely equivalent, we cannot say anything about if they are Legendrian isotopic or not. All right. Now, knots in overtwisted manifold. So there are two types of knots in an overtwisted manifold. They are known as loose and non-loose. They are actually also known as exceptional and non-exceptional. But I will use loose and non-loose. So why there are two types of knots? So if I am in an overtwisted manifold and I have a knot in an overtwisted manifold, the knot can intersect the overtwisted disk, or it can be disjoint from an overtwisted disk, right? So if we remove a tubular neighborhood of the knot from the manifold, the complement can become either tight or overtwisted. Now, how it can become tight? If the knot intersects every overtwisted disk, then by removing the tubular neighborhood of the knot, we are also getting rid of the overtwisted disks. So by removing the knot, we are kind of changing the geometry in some sense. And those are the knots which will be non-loose. On the other hand, if the knot has an overtwisted disk disjoint from it, then by removing the knot, the complement is still overtwisted. So it's not really that interesting, right? So these are basically the definitions. So a non-loose knot will be a knot with complement tight, and a loose knot has over-twisted complement. There are other ways also to define these knots, like surgery definition. So a non-loose knot will be a knot where you do a surgery and you get a tight manifold. Okay. Next are the classification results. So what are the classification results of these loose or non-loose knots? Now, as I will tell you these classification results, you'll see that how these two types of knots are different, and actually you'll see that how non-loose knots are the ones which are the ones very, very interesting and mysterious at the same time. Okay, so the first result is about loose non-homologous knots. These are completely classified by A.K.A. in 2010. So if you have two knots, two loose knots, which are non-homologous, so the Thurston-Banachman and the rotation number are well defined. And if they have the same Thurston-Banachman and same rotation number, then they are coarsely equivalent. So after contactomorphism, they are the same. So the natural question was, what about links? If I have more than one component, is this result still true? And it turns out yes. So no matter how many components we have, as long as the components are null homologous, so that I can define the Thurston-Banachman rotation number for each component. And as long as they are loose, so there is an over-twisted disjoint from them, they are coarsely equivalent. And this is one of the results from my thesis. Okay, so that means loose knots are completely classified, loose links are completely classified, and also this telling us that they are not really that interesting, right? Because they're completely classified. So what about non-loose ones? The first non-loose example, non-loose classification, was due to Ehrlich-Fraser, and this is unknots, of course. So they classified non-loose unknots. And there is also an interesting fact in this paper that they proved, and that is that non-loose Legendre unknots can only be found in this S3 Z negative 1. This negative 1 is the Hoff invariant associated to that over-twisted contact structure. Of course, Hoff invariant or D3 invariant, they are very closely related. S3 doesn't have any D2. So this is very interesting that if you are in any other over-twisted contact structure on S3, by the way, S3 has V worth of over-twisted contact structure. So if we are in, say, Z negative 2 or Z negative 5 S3, then, and you find an unknot there, a Legendrian unknot, that has to be loose due to their result. So this tells us that these non-loose Legendrian knots are rare. You cannot really find them in every over-twisted contact structure. Okay, so this was the first result. The second candidate is, of course, the torus knots. Now, this study for torus knots started with Geiges Unaren. They partially classified non-loose torus knots. And Irena Matkovic, she extended this result, their result, for negative torus knots, but only up to a certain Thurston-Banachman number. And recently, Etnar, Min, and Mukherjee completely classifies non-loose torus knots, and this is a work in preparation. And these are the only two knot types which we have a complete classification. The next is about links. What about links? So the non-loose Hoff links in S3, that is completely classified by Geiges Unaren, and this is a result from 2018. And right now, this is a work in progress where with Geiges and Unaren, we are trying to classify non-loose Hoff links in length space. So we are moving in a different 3-manifold and see how the classification can be different. And all these results, by the way, are only up to contactomorphism. So nothing is here. There is nothing about Legendre anisotropy. So we do not know much about Legendre anisotropy of this classification of these knot types. Okay, so these are the classification results which is known. In the part 2, I will be talking about the structure theorems of these knots. And this is a joint work with Etnarman and Mukherjee. So what do we mean by a structure theorem of Legendrian knots? This basically means that how the behavior of the Legendrian knot changes under this topological operation. And what are the topological operations we are concerned with? They are connect sum, cabling, and Whitehead doubling, or in one word, the satellite operations. So we want to know that how the satellite operation is changing the geometry of these knots, or if they are actually kind of from the pieces of these knots. If we can see, if we can know anything about the composite knot. Okay, so a very brief history. Ednar and Honda actually started the study with connect sum of Legendrian knots in tight manifolds. And what they showed that if the prime pieces are Legendrian simple, then the composite knot is also well behaved. That means the connect sum actually behaves nicely. So that's good. The second one is, of course, the cabling. Again, Etnar and Honda, they continued their study with Legendrian cables in S3Z standard, which is the tight S3. And here, this paper is very, very interesting paper because they also found here non-transversely simple example of non-transversely simple knot type. And later, this continued the study with the Tadbert Tishi, and they actually completed the satellite operations with also Legendrian Whitehead doubles. Okay, so these are the things which we know about knots in tight manifolds, or the satellite operations in tight manifolds. Now, I'll just focus on cables of Legendrian knots. The definition is that a PQ cable of a knot is a knot which has slope Q over P on the boundary of the solid torus, which represents the knot type. And here are the patterns. On the top, this is the positive cable pattern, and where it's like P times along this way and Q times along the meridian. And the bottom one is the negative cable pattern. And as you can see, these two pictures are a little bit different. I had to add the zigzag because in Legendrian setting, we do not have a particular type of crossing. So we have to add this the zigzags for that. Okay. Now in S3 standard, the structure theorems for cables and the Whitehead doubles, they depend on a property which is known as the uniform thickness property. So before I tell you what is this uniform thickness property, I'll give you the theorem, the statement of the theorem, and see how much it is important in their theorem. So in Etnar and Honda's theorem, if the knot is Legendrian simple and it satisfies the uniform thickness property, then the cable is also Legendrian simple. And not only that, it actually admits the classification in terms of the classification of the underlying knot. So this tells us that this property is very crucial for their theorem. So what is this property? Uniform thickness property, a knot satisfies this property if you can take any representative of that knot type and then take the neighborhood of that, and then we can thicken the neighborhood uniformly to its max TB neighborhood. And you cannot go beyond it, so you have to stop right there. Now, max TV is definitely a very specific property of a knot for tight manifolds because we have Benign inequality there, which gives us the max TV. And the problem with this property is that not every knot satisfy this uniform thickness property. In fact, there are a lot of knots which do not satisfy uniform thickness property. And the first example which right now you must be thinking is, what about the unknot? The unknot actually does not satisfy uniform thickness property. So though we know that the unknot is a Legendre simple, and the cables of the unknots are the torus knots. And we also know that actually the positive and the negative torus knots both are Legendrian simple, but it's not coming from this theorem. So they do not admit really the classification in terms of the unknot. So what about the positive or the negative torus knots? The negative torus knots satisfy the uniform thickness property. So the cables of the negative torus knots are also Legendrian simple. But the positive torus knot do not satisfy, positive torus knots do not satisfy the uniform thickness property. So as you can see that the uniform thickness property is not really that common among knots. But what is our problem? Our problem is that we are in overtwisted contact manifold. And in overtwisted contact manifold, we definitely do not have any UTP because we do not have Benign inequality. So we do not have any max TB. So there is no notion of UTP in overtwisted contact manifold. So we cannot use the same techniques as tight manifolds. So now cables of knots in overtwisted manifold. So I guess by now I have convinced you that the cables of knots in overtwisted manifold should not be in the same, the proofs should not be in the same way as they were done in the tight manifolds. So if you are thinking about loose knots, the cables of loose knot, that's very easy because a loose knot always have an overtwisted disjoint from it. So we can always do the cable away from the overtwisted disc, the cabling operation. So the cable is also loose. That's easy and not interesting. The interesting part is the non-loose knots. Why? Because there are non-loose knots where the cables of those non-loose knots become loose. So that's why this is a difficult and interesting problem to see that exactly what conditions are forcing the cables of non-loose knot to remain non-loose. So this is our first theorem. This tells us that if you have a non-loose representative of a knot type in any overtwisted contact manifold, as long as the cabling slope is greater than the Thurston-Benefit number of that knot, for Q and P both be positive, then the cable is also non-loose in the same contact structure. So the TB is the one, or the cabling slope, and the relationship between the TB and the cabling slope is the condition here. Now, how does the proof work? I will not go into the detail of the proof, of course, because it's very technical, but I'll say that we used convex surface theory and a very important tool in convex surface theory, which is known as the state transition technique. So we used that, and we started actually with the assumption that the cable is loose. So if we start with the assumption that the cable is loose, and then by using the state transition technique, we can prove that the knot we started with is loose as well. So that's the in a very brief, like it's a very brief idea of proof, but that's what basically we did. So the next question is, what happens when the cabling slope is less than equal to the Thurston-Benefit number? Now, when the situation can arise, if you're thinking about negative cables, then the situation can arise. So what happens then? So the problem is that the technique which we used for positive cables used the fact that P and Q are both positive. So for negative cable, that technique is not going to work. So how are we going to solve this problem? Well, we will introduce an extra condition. So with that extra condition, our second theorem is that if we have a non-loose representative of a knot which has a non-loose transverse pushoff. And this condition is very, very important for our proof. So it's so when this is true, then for the cabling slope less than equal to the Thurston-Pennington number of the knot, the cable is also non-loose in the same contact structure. So first of all, I should mention here that not every non-loose Legendrian has a non-loose transverse pushoff, and an example will be the unknot. Non-loose, we do not have any non-loose transverse unknot in S3, a result due to A.K.A. pressure. Though we know that there are non-loose Legendrian unknot in S3, but no Legendrian transverse unknot. So our theorem doesn't work for unknots. Okay. So now some future work. It is known that connect sum does not preserve non-looseness, which must be very surprising. At least for me, it was very surprising. That if you take two non-loose knots and you do the connect sum, it suddenly becomes loose. And we have a very trivial example actually. So take two non-loose unknot, which live in S3Z -1, and you do the connect sum operation. It's still an unknot, but D3 invariant or the Hopf invariant, that's additive under connect sum. So it becomes -2. So now the unknot lives in -2 overtwisted, and it cannot be non-loose due to A.K.A. pressure. Also, another example you can think of is the left-handed trefoil and the unknot. The same thing will happen. So our question is, if this is always the case, because we have so little knowledge of these unknots or the classification, and we do not know what knot types live in which overtwisted contact structures, we actually do not know if this is always the case. And also in our examples, one of the candidate is the unknot. So it might be the case that maybe if both of the components are, both the knots are non-trivial, then we can then it can preserve non-looseness, but we don't know. And even if it's always the case that whenever you take two non-loose knots and you make the connect sum and it becomes loose, then why this is happening? So we do not really have a good reason for why this may be the case. Okay. And the next question is about Legendrian Whitehead doubles. Of course, after cabling operation, the next question is, of course, what about the Whitehead doubles? For tight manifolds, the Whitehead doubles, the classification of Legendrian Whitehead doubles, again, rely on this uniform thickness property. And we do not have uniform thickness property. So what can be an obstruction of this non-looseness? We actually don't know. Maybe it is always non-loose, or maybe it can become loose under certain conditions, but we don't know. So there, like, again, you can think about some examples, some very trivial examples. But as we don't know much about these knots, like you have already seen in the classification, like little is known about the classification result. We are right now working on the structure theorem. And as you can see that also this for the transverse pushoff being like for Legendrian, non-loose Legendrian to have a non-loose transverse pushoff is also not common. So that's also a very, we are like kind of constraining there, like it's a constraint there. So there are like lots of questions in this area which are not that much explored, or kind of we don't know much about those questions. And it will be a good place to jump in and maybe find some of those answers. So I guess I'll stop here. Thank you for your attention.